Hello friends, welcome back. Today we see the next part 2, that is the application of first law of thermodynamics for non-flow process. Please go through the previous videos. We cover the basic numericals. In today's lecture we see the difficulty or the different variety in this non-flow process application of first law of thermodynamics. In previous videos we cover all the derivations for each process in detail. Please go through that all the videos. Okay, let's start with the first numerical. An oxygen cylinder of 0.25 m³ capacity contain oxygen at pressure of 30 bar and 293 Kelvin temperature. The stop valve is opened and certain mass of oxygen is used. Measurement shows that oxygen left in the cylinder is at 15 bar pressure and 288 Kelvin temperature. Determine the mass of oxygen used. After closure of the valve, the oxygen remaining in the cylinder gradually attains its initial temperature of 293 Kelvin. Make calculations for amount of heat transferred through the cylinder walls to the atmosphere. It may be pre-assumed that oxygen has density at 0 degree Celsius and 1.01325 bar. Okay, this is the very best numerical for the first law of thermodynamics or application of first law of thermodynamics. These are the applications we also is suitable or useful for your last year BE projects. Okay, how we calculate mass from certain parameter like the pressure, temperature. Okay, these are the very interesting. They given one cylinder, oxygen cylinder having volume is 0.25 meter cube. So what it indicates, it gives me the idea is the numerical on constant volume process. Okay, this is the numerical on constant volume process because the oxygen cylinder, okay, because its volume is the same and its boundary is rigid, so it is the constant volume process. Initially, before relieving valve or before using that relief valve or stop valve, what are the initial conditions? That is given pressure is 30 bar and the temperature is given 293 Kelvin. Okay, when after stop valve is used and certain amount of oxygen is used, after that the final condition of the cylinder is pressure is 15 bar and the temperature is 288 Kelvin, and they ask determine the mass of oxygen used. They are given certain conditions before, what are the pressure, temperature, after stop valve is opened, what are the pressure and temperature. This is very simple. We calculate by using the fundamental formula, that is PV is equal to MRT. Initial mass, first we calculate P1 V1, okay, MR T1, okay, the final mass, that is the P2 V2, MR T2. Okay, so P1 and T1 is with us, P2 and T2 is with us, and the cylinder volume is constant, is not going to vary. So V1 is equal to V2 is equal to 0.25 m³. Okay, the only unknown parameter is R. Okay, for calculating R, they given one hint like the density and the pressure and the temperature. So by using fundamental formula, again I use PV is equal to MRT. For calculating R, initial pressure we take 0 here, no problem. Okay, V0, that is a T0. For calculating R, we get the formula like that. But you know that they given density is equal to mass per unit volume. So that equation becomes now R is equal to P0 upon density into T0. So all the values with us, pressure is given, initial pressure is 1.0132 bar. That pressure is converted into the Newton per meter square, that is multiplied by 10 raised to 5 Newton per meter square. 0 degree Celsius is converted into Kelvin, that is a 273 degree Kelvin. Okay, density is with us, that is kg per meter cube. Very simple numerical. Okay, we just find R here, that is the P upon rho T. All the values are given, we can get the value of R. Initial mass of oxygen, I told her how you calculate, that is initial simple relation, that is characteristics gas equation, PV is equal to MRT. we can calculate mass m1 here. Same we can calculate m2 here. Okay, so the mass of oxygen used, initial mass minus final mass, we can get is around 4.84 kg of mass of oxygen is used. This is a very best example of our application. We also can set up project we made for your gas cylinder. Okay, there we can attach some parameters like a pressure and temperature. From that we can calculate what is the initial mass contained in the cylinder. Okay, after use certain interval of time, that drop in a pressure, drop in temperature, we can calculate the mass used. So what are the we studied in the classroom, you must be go to apply whenever it is possible. Then also they ask heat interactions. Okay, heat interaction, so it is the fundamental formula. What amount of heat is supplied utilized for change in internal energy and work done. It's constant volume process, so work done is 0. What amount of energy is supplied is 100% utilized for engine is increase in its internal energy, so dq is equal to change in internal energy, that is mcv delta t, but the cv is not given. Okay, how we calculate cv, I already discussed this formula now. Okay, just go through the previous slides so you can get idea. Okay, we know the simple relation here, Cp minus Cv is equal to R. If you take Cv is common, okay, Cp upon Cv minus 1 is equal to R. Okay, Cp minus Cv is nothing but again you see here adiabatic index, so gamma minus 1. From this equation we can calculate Cv is equal to R upon rho minus 1. Okay, in this numerical we can put the value of Cv is like that, R upon gamma minus 1, because the Cv is not given, they given hint like R, gamma, and then both temperature is available with us T1 and T2, so we can calculate the heat transfer. Okay, put the value of mass is very important, is the final mass, that is the m2, while calculating heat interaction. Okay, that is the heat exchange, the very simple numerical. Now we move further for the next numerical. A 1.5 kg of nitrogen contained in a cylinder at a pressure of 6 bar. So they are given pressure P1, they are given mass and temperature 300 Kelvin. So given temperature T1, pressure is here, expands temperature 300 Kelvin, expands 3 times its original volume, assuming the expansion process is to be isobaric. Okay, so the given process is isobaric process. Make calculation for initial volume, final temperature and work done by gas, heat added, change in internal energy. The very simple numerical, you have to just, they are directly given the isobaric process. So we keep in mind the different formulas for the isobaric process we also discussed, and they given one hint here, there hint is there, temperature 300 Kelvin, okay, expands 3 times its original volume. So they have given V2 is equal to thrice V1. They given one relation, V2 in the form of V1. Okay, Cp is there and R is there. Okay, first calculate initial volume V1. The V1 is not given, they given directly V2 in the form of V1. So first find out the V1 by simply fundamental relation P1 V1 is equal to Mr T1. From there we can calculate V1, mass is there, okay, R is there, T1 is there and P1 is there. Okay, the value of R is also there, there is no need to calculate. Then final volume they ask V2, so it's thrice V1. Okay, for constant process we know that the general gas equation V1 upon T1 is equal to V2 upon T2. From that we can calculate T2 simply. Then work done for isobaric process, 2 volumes are with us, pressure is there, so we use the relation work done is equal to P into dV. both volumes with us. Then heat added, we know that for isobaric heat added is mcp delta T. M is with us, Cp is with us, both temperature are given. From now flow energy equations, they also has change in internal energy. Okay, so if we see, they ask change in internal energy. It is the net change between Q and W. Okay, so we can firstly calculate Q and W in previous steps. So directly put these values, we can get the change in internal energy, and that value is in the form of positive. So what it indicates, the change in internal energy goes on increases. That positive sign indicates change in internal energy increases. If there is minus, the change in internal energy going to decreases. This is a very basic numerical, fundamental numerical. So you can, hopes you can easily understood. Now we see the next numerical. It is designed to compress 10 kg of gas from 1.15 m³ to 0.3 m³ at a constant pressure of 15 bar. What it indicates, constant pressure of 15 bar. The process is now isobaric process. They given mass, they given volume V1, V2, and the volumes goes on decrease 1.2, 0.3. So it is the compression process. See here, they mentioned during this compression process, the temperature rises from T1 to T2, 20 degrees Celsius to 150 degrees Celsius, and the increase in internal energy. Increase in internal energy, it means that internal energy, that is the du or delta U, is the positive 3250 kilojoule. Calculate work done for isobaric process, heat interaction, that is a dq, change in enthalpy dH. Also work out average value of specific heat at constant pressure. Is again very simple or straightforward numerical. Just apply basic fundamental formula. Work done. Pressure is given, both volumes are given. We can easily calculate work done. Heat interaction is mcp delta T. Okay, so that not given the Cp. Okay, but they given the change in internal energy here. So I use the fundamental formula, work done plus change in internal energy. Okay, heat supplied. The basic fundamental formula, dq is equal to dw plus du, and they directly given du, and we can calculate dw. So there is no need of use direct basic simple direct formula mcp delta T, rather than we use this basic equation. So first calculate work done, that is the p dv, and change in energy directly given. So we can calculate dq like that. See how we solve now. I told first calculate work done. Okay, we get the answer minus what it indicates is work is done on the system, because we going to compress the gas here. Okay, so work is done on the system. So work directly, the answer is correct because the sign is indicates work is done on the system. So negative. Okay, I also told calculate heat supplied, work done is with us, and the change in internal energy increases. Okay, so heat supplied we can calculate 1450 kilojoule. Okay, they also ask change in enthalpy. We know that change in enthalpy dq is equal to dH for isobaric process, because the formula is same for both cases, mcp delta T. So we can calculate change in enthalpy. Okay, but this answer is for mass 10 kg. Okay, though all the values are given here for mass 10 kg. They also are specific heat, but for specific heat we need 1 unit kg of mass or unit kg of mass. So with change in enthalpy divided by 10 kg, we can get enthalpy change per kg is 145 kilojoule. So dH is equal to, we know that fundamental formula again mcp delta T, and they ask specific heat at constant pressure. So dH is with us, dH is with us. Okay, dt is with us, m is with us. For m is assuming 1 kg here, because we get value of dH for, we get in the value of dH for 1 kg. Then average value of specific heat constant pressure, just simply Cp is equal to dH by dt. we can get specific heat at constant pressure. Hopes you understood these three numericals. Okay. Now we stop. In further video, I am going to cover the remaining numerical also. These are the basic applications or non-flow process. Thank you very much.